Part 1. Key Principles. As sugar sits unprotected and exposed, it slowly absorbs water from the atmosphere. This contributes to a problem known as sugar caking. The absorbed moisture leads to formation of liquid bridges between sugar crystals. When the humidity of the sugar's environment changes, the liquid bridges become solid bridges, causing the caking. Sugar caking can reduce consumer acceptance due to limited shelf life. Sugar in its free-flowing state makes it convenient for food applications. But when the sugar cakes, it forms different-sized hard lumps, which are difficult to break, making it inefficient for measuring and formulation. Caking is inevitable, but the rate depends on storage, time, and environmental factors like relative humidity, RH, and temperature. The longer it can be delayed, the longer its shelf life. Sugar caking can impact manufacturers and retailers because temperature and humidity constantly fluctuate throughout the supply chain. And in a domestic setting, containers and packaging can leak, causing the sugar particles to absorb moisture. From the manufacturing process, the sugar contains a small amount of moisture. This is referred to as the initial moisture content, IMC. The IMC can differ depending on the type of sugar. White sugar is relatively dry and has a low IMC, while brown sugar contains molasses and has a higher IMC. The critical moisture content, CMC, of sugar is the point when liquid bridges form, leading to the onset of caking. Once the CMC is reached, too much moisture has been absorbed and the sugar is now clumped and not free-flowing. The CMC of the sugar depends on type of sugar and particle size. Past the CMC is the equilibrium moisture content, EMC. The EMC is the point where the sugar is no longer gaining or losing any moisture from or to the headspace, when the sugar's moisture content is in equilibrium with the environment's humidity. EMC is indicated by weight measurements remaining relatively constant over time. The EMC depends on the RH of the environment. Sugar in a 100% RH environment will have a higher EMC value than sugar in a 75% RH environment. Part 2. Experimental Design. We devised an experimental setup based on 3 independent variables: food, environmental, and packaging. The food variables included white sugar and brown sugar. These differ in IMC and composition. Caking in white sugar was indicated by the formation of flakes, approximately 25 millimeters, which moved as a whole piece during texture testing. Caking in brown sugar was characterized by the sugar forming a large clump that moved as a single mass when shaken. For the environmental variable, we created 3 distinct atmospheric conditions. We used saturated salt solutions to maintain specific relative humidity, RH levels, within the incubators. The 3 RH levels were 100% using potassium sulfate, 75% using sodium chloride, and 50% using magnesium nitrate to mimic ambient RH. A hygrometer displaying both RH and ambient temperature was placed in each incubator to ensure that the target humidity was achieved and maintained throughout the experiment. For 100% RH, pure water can be also used instead of the salt solution. The packaging variable included 3 conditions: open cups with no cover, cups covered with kraft paper, and cups covered with polypropylene film. These materials acted as barriers between the food and the external environment, affecting moisture exchange. Each metal cup contained 3 grams of sugar and was placed in each incubator. In the no packaging condition, the cups were placed without a lid. In the other 2 conditions, the cups were sealed with either kraft paper or polypropylene film. The different covers allowed us to evaluate how different packaging materials influence sugar caking and, ultimately, shelf life. Part 3. Materials and Methodology. Other equipment used in this experiment includes RH meters, tins, customized lids, and scales. The RH meters help keep track of the actual RH in each incubator. If the RH deviates, this can affect the sugar's moisture absorption and must be corrected if it occurs. The tins and customized lids are where the sugar samples will be held and weighed. The customized lids will have either an empty opening or an opening with one of the 2 packagings. During experimentation, all data was collected using 2 scales: a smaller, portable scale, which was less precise, measuring to the 1,000th place, and a larger stationary scale, which was more precise, measuring to the 10,000th place. Both scales accurately measured the changes in mass of the sugar samples. While the large scale is able to collect more precise data, it is impractical, and the smaller scale is able to serve the same purpose. Sugar samples were weighed initially and placed into their respective containers. For the first day, samples were weighed after 2 and 6 hours. After the first day, samples were weighed once every 24 hours for a week. Data was collected manually and put into Excel where analysis was conducted. Part 4, Results and Conclusions. Both the no-lid and paper samples in the 100 RH environment will be able to absorb a lot of moisture and quickly surpass the critical moisture content. However, the paper lids will still act as a barrier and lower the final moisture content of the sugar. The film, on the other hand, is very effective as a barrier, significantly reducing the rate of moisture absorption, even in the 100 RH environment. The samples in the 75% relative humidity environment follow a similar pattern. The no-lid and paper samples quickly reached their critical moisture contents, while the film samples took much longer or never reached the critical moisture content. Now let's see why this is. Each sugar sample, depending on the type of packaging barrier, reaches the critical moisture content, CMC, and subsequently the equilibrium moisture content, EMC, at different rates. Samples without any cover reach EMC more quickly due to unrestricted moisture transmission through air diffusion. In contrast, the other two samples were covered with barriers that impeded moisture transfer. For moisture to reach the sugar in these cases, it had to diffuse through the packaging material. The rate of moisture transmission depends on factors such as the material type, packaging thickness, and surface area. Between the two types of barriers tested, craft paper and polypropylene film, the film proved more effective in delaying sugar caking. While the paper barrier also slowed down caking, it was not as effective as the film. The paper barrier, being more porous and moisture absorbent, allowed moisture exchange at a slower rate, slightly delaying caking. It was particularly ineffective for brown sugar at 100% relative humidity, but performed better with white sugar and at 75% relative humidity for both sugars. In contrast, the polypropylene film was more effective across all samples and RH conditions, creating a stronger moisture barrier and significantly delaying sugar caking. In summary, both RH and packaging significantly affected sugar caking and shelf life. Higher RH, especially 100%, accelerated caking as sugar absorbed more moisture. While paper offered some protection at 75% and ambient relative humidity, it was ineffective at 100%. Plastic film was the most effective across all RH levels. IMC, CMC, and EMC were key in analyzing caking behavior.